Hello, and welcome to today's lesson on the generator effect. In today's lesson, we'll introduce the generator effect, learning how moving a conductor through a magnetic field or changing a magnetic field around a conductor induces a potential difference. Next, we'll discuss factors which affect the size and direction of the induced potential difference and current. Finally, we'll look at practical applications like electromagnetic flow meters, which utilize the generator effect to measure the flow rate of conducting fluids. So far, we have explored the fundamentals of magnetism and electromagnetism, including magnetic fields and forces on charged particles. Building on this foundation, we can now delve into the generator effect, enhancing our understanding of how motion and magnetic fields interact to produce electrical energy. This lesson will link fundamental principles to practical applications, broadening our understanding of electromagnetism in real-world contexts. Let's get started. First, let's understand what the generator effect is and how it works. The generator effect, also known as electromagnetic induction, occurs when either a conductor moves through a magnetic field or the magnetic field around a conductor changes. This action induces a potential difference or voltage across the conductor. If the conductor is part of a complete circuit, this induced potential difference will cause an electric current to flow. One common demonstration of this is moving a wire between the two poles of a horseshoe magnet. As you move the wire quickly up and down through the magnetic field, a potential difference is induced in the wire. If the wire is part of a complete circuit, an electric current will flow. The faster you move the wire, the greater the induced potential difference and the resulting current. Another method to observe the generator effect involves moving a bar magnet in and out of a solenoid, which is a coil of wire. When you move the magnet, the changing magnetic field induces a potential difference in the solenoid, which can be detected by a galvanometer. As before, a faster movement of the magnet results in a greater induced current. Moreover, if you reverse the direction in which you move the magnet, the direction of the induced current will also reverse. When a current is induced in a conductor, it generates its own magnetic field. For example, if you move a magnet towards a coil, the induced current in the coil will generate a magnetic field that repels the approaching magnet. Now let's look at factors that affect the size and direction of the induced potential difference and current through a conductor. We'll start with the four factors that affect the size of the current. First, we have the speed of movement. The faster the conductor or magnetic field moves, the greater the induced potential difference and current. That is, if you increase the speed at which you move a wire through a magnetic field or a magnet through a solenoid, you will see a corresponding increase in the induced voltage and current. Next is the strength of the magnetic field. A stronger magnetic field induces a greater potential difference. This is why strong magnets are often used in generators and other electromagnetic devices. They produce a larger induced voltage for a given speed of movement. The third factor is the number of turns in the coil. If you are using a solenoid, increasing the number of turns in the coil will increase the induced potential difference. Each turn of the coil experiences the magnetic field change, so more turns mean a stronger cumulative effect. Finally, we have the area of the coil. A larger area of the coil exposed to the magnetic field results in a greater induced potential difference. Essentially, a bigger coil can intercept more of the changing magnetic field lines, leading to a higher induced voltage. Now moving on to factors affecting the direction of the induced potential difference and current. There are two key factors to remember. First is the direction of movement. Reversing the direction of movement of the conductor or the magnetic field will also reverse the direction of the induced potential difference and the current. This is because the motion is now cutting through the magnetic field lines in the opposite direction. Secondly, we have the orientation of the magnetic field. Changing the orientation of the magnetic field relative to the conductor will change the direction of the induced potential difference and current. For instance, if the direction of the magnetic field is flipped, the direction of the induced voltage and current will also flip. Let's now take a look at a practical application of the generator effect. An electromagnetic flow meter is a device used to measure the flow rate of a conducting fluid, such as water. It consists of a pipe through which the fluid flows, electrodes placed on opposite sides of the pipe, and a magnetic field applied perpendicular to the flow. As the conducting fluid moves through the magnetic field, it cuts across the field lines, inducing a potential difference across the fluid between the electrodes. The magnitude of this induced potential difference is proportional to the speed of the fluid flow. By measuring the induced voltage, the flow rate of the fluid can be determined accurately. In today's lesson, we delved into the generator effect, exploring how moving a conductor through a magnetic field or changing the magnetic field around a conductor can induce a potential difference, leading to an electric current if part of a complete circuit. We also discussed how the induced current generates a magnetic field that opposes the change in the original magnetic field, before reviewing the factors which influence the direction and size of the induced current and voltage. Finally, we looked at practical applications like electromagnetic flow meters, which utilize the generator effect to measure the flow rate of conducting fluids. Understanding these principles is crucial for grasping how electromagnetic induction is used in various technologies and applications. Watch the rest of the GCSE Physics course at Sophos Education.